Okay guys, I'm back in the normal lab away from that fume cupboard which doesn't really ventilate that well. Okay, anyway, I'm here. I brought some concentrated hydrochloric acid with me. This one looks a bit disgusting, a bit yellow. To be honest, I don't think they are super concentrated anymore. They might have been very, as in like most of the HCl fumes might have just escaped over time. I'm not sure how old they are, but we'll try and do some cobalt chemistry with them. So what I have here is 2 cobalt salt. This is cobalt chloride. It's a hydrated salt. I talk about it in the other tutorial videos on water crystallization. Okay, so it's kind of like dark pink solid. The other one I have is a cobalt 2 nitrate. So just now was cobalt 2 chloride. This is cobalt 2 nitrate. It's also a hydrated salt, so it's got water crystallization. This is a bit disgusting, so some of it has already kind of like the water has come off, but if you could hear me doing, so there's most of it is still crystalline solid at the bottom, and it's just the water crystallization that has come off. Okay, so what I'll do is I'll make up a solution, so using a test tube, a boiling tube or whatever. So I'll just have a cobalt chloride. I don't need too much of it. So I'll just take out a little bit of that pink solid, and I just want to show you what happens when I heat this pink solid. So this is a hydrated cobalt chloride. A hydrated cobalt chloride. I need to find a test tube holder. No, I can't. I don't want to be heating up boiling tube because the test tube holder is quite small. So I'll scoop out a little bit more of the solid. When I say small, I mean it's like my test tube holder is a bit tight, so they're not that. The test tube holder is a bit tight with the really big boiling tube compared to the test tube. So this is a pink solid. We will heat it. If I heat the pink solid, it's a hydrated salt. So first thing that comes off will be the water of crystallization. Hope you can see now it is blue, just now was pink. There's a bit of condensation on the upper part of the tube, and if I heat it further, it will become more obvious. It's the water crystallization that is coming off. So the water crystallization is coming off, you get a colorless liquid formed on the upper part of the tube. Hot end, cold end, water crystallization escape as steam, and when they reach the cold end, they will condense. You get a colorless liquid. This was a colored compound, so it all makes sense hopefully. So hydrated cobalt 2 chloride was pink in color, and this is what you call, this blue color is what you call anhydrous. Anhydrous because you remove the water crystallization and it's blue. So what happened with this blue color solution is if I add water to it, it will become hydrated again, and we use anhydrous cobalt 2 chloride paper, which is filter paper coated with this anhydrous cobalt 2 chloride to test for water vapor or water, and it will turn pink. I'll wait for a bit until it cools down before I add water to this hot glass test tube. It's very dangerous to add water to a hot glass test tube. Okay. So what I have, however, is this other test tube containing the solid. So this one was cold to begin with. If I just add distilled water to it, you see this is a cobalt 2 plus with water around it. Okay, cobalt 2 plus with just 6 water around it. So this is cobalt hexaaqua complex. This is actually cobalt 2 hexaaqua complex. Hexa because there are 6, aqua because it's water as a ligand. if you are an A-level student, you will really know what the ligand really means. So the H2 has got lone pairs on the oxygen. They form the active covalent bond to the transition metal center. A pink color solution, okay, for cobalt 2+. So what I'm going to do is I'll divide them into separate portion. I'll test with sodium hydroxide. I'll test with ammonia. And then I want to try and add some hydrochloric acid to it and see what happens, okay? So first off, let me try by adding some sodium hydroxide. Aqueous sodium hydroxide, so there's NaOH. So what happened with the cobalt? This thing is really bad. Might just pour it actually. It's not a good idea. So this is clear solution. I'm going to add sodium hydroxide, which is also a clear solution. And you get this color here. So this is a precipitate, because if I swirl it, so this looks a bit like the color of my shirt. So this looks a bit like, so this background here, so this is a blue precipitate. So this is cobalt 2 hydroxide, because it was cobalt 2+. You can see it's a precipitate because if I swirl it around, some of the solid gets stuck on the side there. So they are not soluble at all. So it's not a see-through, it's not a solution. You get a blue precipitate from the pink solution because the cobalt 2+ surrounded by 6 water around the cobalt 2+ has now precipitated out as cobalt 2 hydroxide. So there's CO2+, 2 OH minus. So there's cobalt 2 hydroxide, cobalt OH twice, okay? How about when I add excess sodium hydroxide to it? So does it dissolve in excess sodium hydroxide? When I add excess sodium hydroxide to it, I hope you can see it's still like a suspension, but the solid is not entirely dissolved. It looks like it's dissolving, but if you look closely, okay, I better go and get a white background. So if you look closely, there is like a suspension. It looks dark, but there is a suspension of solid within. So sometimes a lot of students think this is soluble, but if you let it settle for a bit, you will see that the solid suspension remains insoluble at the bottom. So it was when you add sodium hydroxide to cobalt 2+, aqueous ion, that means with the 6 water around it, it precipitated out as cobalt 2 hydroxide. You saw a blue precipitate, and then it's insoluble in excess sodium hydroxide. Okay, so what next can I do? I can add some ammonia to it. So start from the pink color solution again. What I have here is aqueous ammonia. So this is not a concentrated ammonia, this is just your bench reagent. So what happens when I add ammonia? So you get the blue precipitate as well, but I hope you can see that they were kind of two different shades of blue. This was more dark blue, darker, and this is more, it looks a bit like a greeny blue. The kind that looks like my shirt from the other day, the other video actually, but I'm not wearing that shirt at the moment. So this is what you call a blue precipitate as well. When I added ammonia, when I added aqueous ammonia to this solution containing cobalt 2, you could see the precipitate color on the upper part of the tube, because when I shake it, some of the precipitate, they stay on the upper part of the tube, and they are insoluble definitely. So this is a precipitate. Okay, this is a blue precipitate. What happened when I add excess ammonia to this solution containing cobalt 2+? Still insoluble. How about if I add excess ammonia? It is still insoluble. Okay, just like the sodium hydroxide case just now, there is like a suspension. Better close this thing first. So the cobalt 2 plus in NaOH, you saw they already settled down. If I don't swirl it, this was with sodium hydroxide in excess. The solid is insoluble. You see the solution on top. This was in excess NaOH. The precipitate was insoluble in excess NaOH. This was like a green-blue precipitate in aqueous ammonia. I added excess aqueous ammonia and it is still insoluble. The suspension, I hope in a little bit it will become clearer. It's like suspension. This is excess ammonia. Okay, not too sure how clear it is, but it's a suspension because the solid, the precipitate remains insoluble. Two different color. This was in sodium hydroxide, this was in ammonia. There are different shades of blue, and this is different from the blue color that you get when copper 2 plus in excess ammonia looks like. Okay, so they look different from those dark blue or deep blue color. Okay. What I'm going to use, however, for this tutorial video is a similar kind of compound. It's a cobalt 2 chloride. So this is also a hydrated compound, even though it doesn't say it's hydrated. But as you could see from the formula, Cl2.6H2O. So it's got water crystallization, and this is called hydrated cobalt 2 chloride, or it's called cobalt 2 chloride hexahydrate. It's a perfectly kind of pink. Well, it doesn't look very clear there because of the contrast, but let's shift our focus onto the practical bit of this tutorial video. So okay, grab a clean spatula. So this is clean, alright, and what I put in there, as you can see, is this pink color. You should get a white background. Is this pink color kind of solid. So this is cobalt chloride hexahydrate. It's pink color kind of solid. Alright, so this is a test tube, so it's dry. Okay, I'll put a little bit of it into another test tube because I want to show you what happened when I hit them. Okay, so this is also cobalt chloride hexahydrate. So there will be a cutback to a different tutorial video where I actually heat this up, and I will get a blue color solid as a result of heating this hydrated salt. It will get rid of the water of crystallization, and what you will get is no longer this pink color hydrated cobalt 2 chloride, but you will get the blue colored anhydrous cobalt 2 chloride. So that's the one where the water crystallization has been heated off. So to be cut back to that video. So we're ready to start this qualitative analysis. So I have a bottle of distilled water or deionized water. I will dissolve this cobalt 2 chloride hexahydrate in water, and what we'll get is a pink color solution. So they're not very soluble because they are solid. So I might have to swirl it around a little bit harder. They're slowly dissolving. So it looks like almost all of them has gone. Okay, I have a little bit more of that cobalt chloride that I poured just now. I was supposed to show you a cutback to a separate tutorial video which I had taken another time. That was to do with the heating up the hydrated cobalt 2 chloride, and they're supposed to show the pink color solid going to blue, and you have seen that in the other section of the tutorial video. So this is cobalt 2 plus surrounded by 6 water molecules. A-level students will know that this is a cobalt 2 complex. It's a hexa-aqua complex. So pink color solution. I will divide it into separate portion. First portion here, second portion here. I should use another different tube. Okay, so first of all, I want to add a little bit of sodium hydroxide. So sodium hydroxide is a base. What happened when I add sodium hydroxide to this? is that we will see you get a blue color precipitate. So I don't know, against the background, this background is probably as good enough. So you do get a blue color precipitate in contact with sodium hydroxide. So there's cobalt to hydroxide. It's a precipitation reaction. And of course, what happens when you add the cobalt, well, when you add the sodium hydroxide in excess, the blue color become more apparent. So there's the blue color become more apparent, and obviously you could see that the precipitate remains insoluble in excess sodium hydroxide. I've added quite a lot of sodium hydroxide now. This is cobalt 2 hydroxide. It precipitates out as a blue colored solid. Sorry about the camera angle. Precipitate out as a blue colored solid. Alright, so there's insoluble in excess sodium hydroxide, NaOH. Now I'm going to try and add a little bit of ammonia to it. Ammonia, aqueous ammonia, NH3. So we'll see what happened here. We get a similarly colored precipitate, but they look slightly different. This is a bit a darker shade of blue, a different shade of blue, but it's still a precipitate. As you can see, some of them get deposited on the side of the tube. I may need to add a little bit more because I think I had quite a lot of the cobalt 2 plus salt dissolved in water just now. So perhaps the color will become clearer when I add a bit more, and it does become clearer when I add a bit more ammonia, and the precipitate remains insoluble in excess ammonia as well. So as you can see, this was in ammonia. It's kind of like a different shade of blue. This was in excess NaOH. This is what ChemGuide had mentioned on the website. It started as a blue thing, but they turned out to be a little bit of pink color style on top. But ideally speaking, we always consider the cobalt 2 hydroxide to be a blue colored solid that remains, in excess NaOH. And this is the a different shade of blue. We call this blue as well, blue precipitate. But as you can see, they're different color kind of blue that remain insoluble in excess NH3. Now this is still the cobalt with just water in it. What I'm going to do is, I think the last time I tried this, I had a bit of acid which was no longer fuming or concentrated. What I have here is a hydrochloric acid. So hydrochloric acid, concentrated hydrochloric acid, is colorless. I don't want to be breathing it in, so I will add a little bit of it to this pink color solution. Let me go and grab a test tube holder. And I'm back with a test tube holder because we don't want to be spilling the corrosive acid on our hands. Alright, so adding a little bit of concentrated hydrochloric acid to this pink color solution. The concentrated hydrochloric acid has a lot of chloride, Cl-, that can help to replace the H2O molecules, and you will see what happened hopefully. Okay, I hope the color changes is quite clear. It's very distinctive, isn't it? Okay, so it's gone kind of like blue color, very nice blue color there. So it's gone from pink, which is the hydrated complex, to this very nice blue colored complex, which is basically cobalt with cobalt 2 plus with 4 Cl- around it. So now it's Cl 2 minus, and to counter you also have a CO2 plus, and of course you have a CO2 plus and Cl 2 minus. The stoichiometry is still correct, it's still cobalt chloride. Okay, so ideally speaking, when you have heated the hydrated cobalt 2 chloride, you get anhydrous cobalt 2 chloride, which is kind of like blue, purple or blue in color. Okay, this is just a deeper shade of blue, so all of them looks blue, but it's a different shade of blue. This is the color of cobalt with 4 chloride around the cobalt 2 plus, therefore CO2 plus and 4 Cl minus, giving you Cl 2 minus. Alright, so that was just on their own. I added the ligands, sorry, the substance itself. I have a little bit of cobalt 2 plus solution here. What I want to show you now is just a very simple reaction. This is sodium carbonate, Na2CO3 is a solution. All sodium salts are soluble in water. So carbonate tends to precipitate out transition metal ions because they tend to form insoluble carbonate. So this is CO2 plus aqueous. Ideally speaking, I should be able to get the cobalt 2 carbonate. Let me see. As you could see, they do precipitate out the two aqueous solution, which is soluble and soluble. Now you get this really nice pink color kind of precipitate. So there is cobalt 2 plus, CO3 2 minus. There is cobalt 2 carbonate, COCO3. Just like a lot of the group 2 carbonates, just like a lot of the other transition metal carbonates, they precipitate out as insoluble precipitate. Okay, so if you write ionic equation, it will be CO2 plus aqueous plus CO3 2 minus aqueous becomes COCO3 because of the 2 plus and 2 minus of the ions. Then you get this precipitate as a solid. So we have this very nice color for the chloride complex. We have this very nice color for the cobalt 2 plus with 6 ammonia around the compound, around the complex. We have this supposedly should be a blue precipitate to start with, but on standing it's gone a little bit pink. But initially, remember when we first started with hydroxide, it was a blue solid that remained insoluble in excess. I'm going to try and use the concentrated hydrochloric acid to try and push an equilibrium. So here we have the cobalt 2 hydroxide which precipitate out. What I would do is I'll add some hydrochloric acid to it, which first of all will neutralize the sodium hydroxide that was present, and secondly it will try and replace the hydroxide with Cl minus, and therefore we should be able to get to this cobalt chloride COCO4 2 minus complex. But let's see. Okay, so this is the cobalt 2 hydroxide precipitate that has gone a bit pink when I left it on standing. I'll add hydrochloric acid, corn hydrochloric acid to it. Not much change because first of all it needs to neutralize the sodium hydroxide that was present. But then the solution has gone pink. You see it's dissolved all of it again. Probably it is because when you neutralize something, you also produce water. A lot of water being produced would bring it back to cobalt 2 plus surrounded by water. So what I'll do is I'll add some more hydrochloric acid. And it hasn't changed much again. It's slowly going towards blue though. The pink color is slowly fading away. So I'll add more. Okay, so you can see it's gone a little bit blue now. Should probably have it on a white background. Okay, it's gone a bit less pink. I think the next bit. So you're competing. The Cl minus is competing with the H2O molecules. And you could see it's gone more purple and more blue. If you get a little bit of pink and blue, they do look a little bit like purple shade like that. So we are sure that the cobalt 2 hydroxide is no longer around. Instead, what we have is the cobalt chloride complex, COCO4 2 minus complex, which has gone towards that side of the equilibrium. Okay. So I still have some acid remaining. Not a lot. Okay. This is the cobalt with 6 ammonia around the 2 plus. So we'll try and do similar kind of thing. But maybe I should really try and split this up because there's a lot of solution there. So this is the same thing, the precipitate, the cobalt with 6 ammonia around the complex. I'll add concentrated hydrochloric acid to it. So first of all, it fumes because the HCl is being neutralized by the NH3 that was present in excess. So the fumes being formed, they are most likely the ammonium chloride. This is your case study from diffusion, states of matter, the very common case study. What you notice is the solution is now a solution, it's no longer precipitate, and there's a result of the NH3 being taken away, being neutralized by the H plus. And then now you have a lot of water remaining, and the water has gone back onto the cobalt 2 plus, giving you the hexa aqua complex, which is pink in solution. So supposedly I add more concentrated hydrochloric acid. As you can see, the solution has gone less pink, it's gone more blue, and that's a result of the equilibrium favoring the formation of the tetrachloride, the 4 chlorine around the cobalt 2 plus. So I can try and force it even more, and it would look even more blue. Okay, so a little bit of pink, a little bit of blue. That's because everything is in equilibrium, but you can force the equilibrium to go all the way to the cobalt CO4 2 minus complex, which, you know, when it's very concentrated, it's supposed to look like this. Okay, this was without any NH3, without any hydroxide in there. It was just hydrochloric acid, corn hydrochloric acid with the cobalt 2 plus hexahydrate complex. Okay, there's a final reaction that I wish to show you. That's basically this cobalt NH3 hexaamine is a cobalt with 6 NH3 around the 2 plus. We'll just do a little bit of sodium, sorry, not sodium, we'll just do a little bit of oxidation on this. This is cobalt 2 plus with 6 ammonia around it. It's a very commonly asked question for electrochemistry. This is hydrogen peroxide, H2O2, 20 volume, so quite a concentrated hydrogen peroxide. So what happens when you add hydrogen peroxide to this is that you will oxidize the cobalt 2 plus to cobalt 3 plus. So I want to be adding just a little bit. So as you can see, there are effervescence, they are bubbling. There's a rapid change in color, and the bubbling indicates gases are given off. Hydrogen peroxide acts as an oxidizing agent. It oxidizes the cobalt 2 plus surrounded by 6 ammonia to cobalt 3 plus surrounded by 6 ammonia. So cobalt 2 plus with 6 ammonia has gone to cobalt 3 plus with 6 ammonia, and it's kind of a dark brown kind of color. Okay, so there's a redox reaction going on because this has acted as an oxidizing agent, which means itself get reduced. So you can imagine which gas has been produced, and you can suggest which gas has been produced based on what has been reduced, because oxidizing agent oxidizes the cobalt species to cobalt 3 plus surrounded by 6 ammonia, and itself get reduced. Alright, that's it really. There's a range of reactions on cobalt chemistry. So I think my test tube has already cooled down. Remember, I had the hydrated cobalt 2 chloride, which was pink, and also pink in solution. Now this was the heated one. Some of it has turned a bit pinkish because of the water vapor in the atmosphere. So this is cool now. I can add distilled water to the blue color solid, which was supposed to be anhydrous, because I drive off the water crystallization. And you notice that the solution again is pink, because in the presence of water it gets hydrated again. Obviously when you add water, then the H2O act as a ligand and surround the cobalt 2 plus, and you get the cobalt hexaaqua complex, cobalt 2 hexaaqua complex, which you could test for other things again. Alright, what I'm going to do next is I'll try and add some hydrochloric acid. In the other earlier videos on the copper 2 chemistry, I was doing it in the other fume hood, which was not working actually. Supposedly concentrated hydrochloric acid is very corrosive. It can give off corrosive fumes, toxic fumes, very bad for you. So a lot of these ligand substitution reactions, they are actually reversible, they are in equilibrium, meaning to say Le Chatelier principle applies, meaning to say when we think about concentration changes, we can shift the equilibrium from one side to the other, and you can catch up more on equilibrium, chemical equilibrium in the AS in the AS chemical equilibrium topical playlist, where I talk more on Le Chatelier principle, not just on temperature, pressure, but also concentration changes. Okay, so that's it for me in these Cobalt 2 case studies. Perhaps I can show you another one actually. So this is Cobalt 3 nitrate, hexahydrate. It's also kind of pink. Remember that I said the solution was like that. but I could scoop out the other thing, and they will give me the exact same kind of chemistry because it is still cobalt 2. So once I scoop it out, it's also like pink solid that kind of like look disgusting because the water crystallization has come off. So most likely they provide you as a solution. As you can see, it's also a pink color solution. Pink color solutions. When I add ammonia, I get a different color. When I add hydrochloric acid, so COCl4 2- is also the same color as the cobalt 2+ with 6 water around it. I've just added ammonia to it, and you get a blue precipitate, and this blue precipitate is insoluble in excess ammonia, as I showed you earlier. When I did it with sodium hydroxide, I also get a blue precipitate that is insoluble in excess sodium hydroxide. And in both cases, I can form another different complex by using concentrated hydrochloric acid to take away and replace the water molecule or the ammonia molecules or the hydroxide with a chloride ligand, and I could get back my pink color solution because there's also the color of the COCl4 2-, CO2 plus 4 of the Cl-, that means +2 - 4, giving you -2 overall charge of the complex. That's it on the cobalt 2 chemistry. Together with the copper 2 chemistry, these two are the backbone of the A2 transition metal case studies in A-levels Cambridge International. Okay, so I will do something after this, but that's it from me in this tutorial video. I'll see you in the next tutorial videos. Don't forget to subscribe to the channel and share the channel widely with all your friends, your chat group, your study group, your juniors and your seniors, and this could be used as a teaching material to further understand equilibrium or to further understand transition metal chemistry in terms of the color changes. That's what makes transition metal very interesting, in particular for myself, because I was very excited about all these color changes when I was a student myself. So do follow me at ptet.chemistry. That is ptet.chemistry on Facebook, Instagram, Twitter, if you're on this social media platform, or when you do return to term in the future after you finish exam. Thank you for watching. I'll see you in the next tutorial video. And I'm back. So basically there is one more reactions of cobalt 2 that I forgot to show. Cobalt 2 is actually pretty prone to oxidation. I think it's the cobalt 2 with the ammonia that is pretty prone to oxidation. So I'm going to remake that solution, that precipitate just now. So I need a bit of my cobalt 2, doesn't matter, cobalt 2 nitrate, which was also pink, or cobalt 2 chloride, which was also pink, in solution. So that is just your cobalt. This is just your cobalt 2+ with 6 H2O around your complex. So there is your hexahydrate complex in solution. I will just very quickly add some distilled deionized water. I get my pink color solution. Just want to make sure that all the solid disappear. Well, all the solid dissolve. Okay, pink color solution. I added my ammonia, and I get my precipitate like this. Okay, so we knew the precipitate was insoluble in excess, as I showed you in the earlier video. Does not matter. Okay, so what is important here really is this is still cobalt 2+ with 6 NH3 around it. What we're interested in is I'll add something called hydrogen peroxide, H2O2. So the oxidation state of oxygen is always -2 when it forms compound. When it's an element, it's 0 oxidation state. When it's a peroxide, the oxidation state of oxygen is -1. Okay, so I have hydrogen peroxide here. It is a colorless liquid. It's pretty strong. Yeah, this is a 20 volume hydrogen peroxide. Okay, so I'm gonna add straight away, and hopefully we'll get a reaction. You see the bubbling? The bubbling is more slightly, I don't know what the result of the bubbling actually is, but what do you notice about the very nice blue precipitate that was insoluble in excess, NH3, it has gone kind of browny, dark brown, really difficult to see, but very disgusting color now. So this is actually cobalt 3+ with 6 NH3 around it. So this is a red, it must be a redox reaction because the cobalt 2 plus goes to cobalt 3 plus. There is oxidation, but the 6NH3 still remains around the cobalt ion. But what must happen is there must be a reduction happening, most likely with the hydrogen peroxide. In fact, it will be with the hydrogen peroxide because the hydrogen peroxide was acting as an oxidizing agent. Itself will be reduced. When hydrogen peroxide get reduced, we are expecting, what do you expect? Okay, so it's oxygen minus 1. Oxygen minus 1 going to oxygen gas is oxygen 0. There must be oxidation. So we're expecting the oxidizing agent, which oxidizes cobalt 2 plus, which was the cobalt 2 plus with 6NH3 around the complex, around the metal ion to give you the complex, to give you this brown color precipitate. It's actually a precipitate, by the way. Okay, it's not a see-through. You could see like a bit of the brown solid on the side there. So this is a brown color precipitate, and this is cobalt 3 plus with 6 ammonia around the cobalt 3 plus, and this cobalt 2 plus has been oxidized to cobalt 3 plus, so the hydrogen peroxide must have been reduced. The idea really is to decide which species gets reduced, and you did see an effervescence just now. That means there were bubble of gases. That means you could have tested for the gas as well. Okay, I leave you to find out what those side reactions, well, not really side reaction, what that reaction was, but the overall reaction really is the cobalt 2 plus being oxidized to cobalt 3 plus. And does it work without the ammonia? Okay, so I'm gonna redissolve that, the one that, remember there were two cobalt 2 plus salt that I have here, cobalt 2 nitrate as well as cobalt 2 chloride. The cobalt 2 chloride is the nicer one to scoop out. The cobalt 2 nitrate is already pretty liquidish, not because it's melted, but because the water of crystallization has come off, and when the water of crystallization has come off, it will come off as liquid water. So this is a solid. Again, I dissolve it in water. I just want you to see, this is the hexa-aqua complex. Will it be oxidized easily in the presence of hydrogen peroxide or not? Just now was the one after I added ammonia, and then I get a blue precipitate which was insoluble in excess ammonia, and that could be oxidized by hydrogen peroxide. This is just cobalt 2 plus surrounded by 6 water. I'm still going to add hydrogen peroxide, but this time to this cobalt 2 plus with 6 water around it. Don't spill it onto my hand. No reaction at all. No bubbles, no changes in color. It's still pretty pinkish. Perhaps you can't see it very clearly. Still pretty pinkish. So what does this tell you? This tells you that ligand, whether you are H2O, which is present in the aqua complex, or when you are NH3 cobalt 2 plus with 6 NH3 around you, the ligand changes the redox potential ability, because whether a redox reaction happens or not, whether it's feasible or not, whether it's spontaneous or not, depends on the E cell value, which is the cell potential, which is to do with the reduction and oxidation. The fact that it happens means that it's feasible, it's spontaneous, but only in the presence of the ammonia ligand, but not the water ligand. So this tells you that ligand will affect the reduction potential, the ability for that cobalt 2 plus to be oxidized by this H2O2, whether it's H2O ligand, which was not possible. When it was NH3 ligand, it was possible to do it at room temperature and pressure. Okay, I have not really done under standard conditions, but the value given in the data booklet on electrode potential, those are all standard condition value, and these are very popular A-levels electrochemistry theory kind of question. Alright, that's it really. So there was just a bit that I was missing out on Cobalt chemistry, so I guess after this then you will hear my ending part of this tutorial video. I've kind of inserted this in between what I finished already just now and my ending part about supporting the channel. So yep, signing off again. So thank you for watching.